Greetings, students. In this video, we are going to study the concept of kinetic energy and work, or rather more importantly, the work-kinetic energy theorem. Perhaps we are all familiar with the classic equation that describes the kinetic energy of a single particle or a single object, which is as following. Ke is equal to 1 over 2 mv squared. Now, Ke is the kinetic energy of the particle or the object, m is the mass of the object, and v is the speed of the object. Let us say we are interested to know the change in kinetic energy when the particle travels from one point to another point on a path. Let's say we have an arbitrary path like this, and let me label the points. Let us say the starting point is at here, which is P1, and the final point is here, P2. Now we are interested what will happen to the kinetic energy when the particle travels from P1 all the way to P2. That is, we are interested to find delta Ke. What is delta Ke? Now, to find delta Ke, we have to do some mathematics. So, first of all, let us take the time derivative of the kinetic energy. But before that, we have to express the kinetic energy in another way. That is, we can write kinetic energy as this: 1 over 2 m velocity vector dot product with the velocity vector, because they are the same, they are equivalent. The scalar v squared can be written as a dot product of two velocity vectors. Now, we take the time derivative of the kinetic energy, that is, dke divided by dt is equal to 1 over 2 m. Now we take the product rule. All right, so in differential or in differentiation, we can take the product rule. So that is the acceleration dot the velocity itself plus the velocity itself dot the acceleration. Now we can sum these two because they're identical. It's a dot product, not a cross product. So the variables can be interchanged. Therefore, it's okay and it's fair to just sum them up. That is, we get 1 over 2 m 2 acceleration dot velocity. Now these two cancel each other. What we are left with is m acceleration dot velocity. Now we know clearly that mass times acceleration is nothing but force. Remember, the time derivative of velocity is nothing but acceleration. So we can write down as force dot product with velocity. Furthermore, we can write down the velocity as the rate of change of displacement. All right, so that is, we can write down as force dot dr divided by dt. Now that was dke divided by dt. So if I bring it down, dke divided by dt. Notice that we can cancel a dt from both sides. So what we are left with is, of course, dke is equal to the force dot product with the displacement vector, or rather the infinitesimal displacement vector. Now, if we take the integral, we can calculate the change in kinetic energy for that path, for that arbitrary path. In fact, it can be used for many or any path. All right? whether it's small or large when we move on the path. What I mean by small or large, that means a small distance or a large distance. All right, so let's take the integral from point 1 to point 2. That is dke. It's equal to the integral from 1 to 2 f dot dr. Now we can write down the left-hand side of this equation as ke2 minus ke1, which is equal to integral from 1 to 2. That means from point 1 to point 2. All right, it's just a generalization of this integral. So the force dot dr. Now the right hand side of this equation is nothing but work. So this is the work. So therefore we have just derived that the change in kinetic energy is nothing but work. So in other words, to move the particle from point 1 to point 2, we have to apply a force. That is the work. We have to apply a force along that path, along that infinitesimal displacement vector dr. All right, from point 1 to point 2. And that gives us the change in kinetic energy, which is also equal to the work. Now let's take an example. Now, suppose we have a force vector in Cartesian coordinates, of course. Let us say it's equal to y, I unit vector, plus 2xj unit vector plus 0k unit vector, all in newtons. All right. Now, let us say we have a path in Cartesian coordinates. Let's say, let me just draw the axes. X-axis, this is x-axis, and this is the y-axis. Suppose we have a path like this. All right, let us call this path as A. All right, let us label the point that, you know, the head that is heading to, which is the final point. Let us say it is 1, 1. That is this point. Let me change the color. This point is point 1, 1. All right. And of course, we are starting from P1, or rather, let me call it as O, origin, 0, 0. All right. Now, this path can be just expressed as the path A can be expressed y is equal to x. All right. Notice that O is 0, 0, moves to P. The particle moves from this point to this point, 1, 1. We see that x is changing, and also y is changing. So they are both changing. Okay. What we have to do in this step is to write down the differential vector, or the infinitesimal displacement vector. For Cartesian coordinates, it's this. dr is nothing but dx I unit vector plus dy j unit vector plus dz k unit vector. We do not have a dz because there is no point to describe, you know, any z part or any z axis. So I'm going to cancel this part, just writing down dx I plus dy j. This is dr, by the way. All right. But remember, y is equal to x. So if we differentiate both sides, we have dy is equal to dx. So either way, we can substitute in dy as dx or dx as dy. I'm going to substitute dy with dx because dy is equal to dx. That means we therefore have dr is equal to dx I unit vector plus, again, because dy is equal to dx, dxj unit vector. That is my infinitesimal displacement vector, or the differential vector. Remember, it's only dependent on dx. That is, we are only moving from 0 to 1. We neglect y, the y part. All right? Now we have dr as this, and we have the force vector, which is yi plus 2xj plus 0k. Let's write it down again. Force is equal to yi plus 2xj plus 0k. But I have to be careful that y is equal to x. So I can substitute any y with x. So that means we can write down this y. I can interpret this y as x because y is equal to x. So plus 2xj plus 0k. This is my final force vector, which basically can be used to take the dot product with dr, so that I can be ready to calculate the integral or take the integral to calculate my work or the change in kinetic energy. Now, the equation work, which is equal to the change in kinetic energy, is nothing but the integral, all right, from point 1, point 2, force dot dr. All right. So let us take the dot product, then we put this dot product back into this integral, and we take in the integral. All right. So let's take the dot product, f and dr. So if we take the dot product, we know that xi multiplied by dxi, we get just x dx. The I components, unit vectors, will be just, multiplied into 1. Okay, plus 2x multiplied by j, here, this one, with this one, we get 2x dx. 2x dx. Now we can sum these two. We can easily get 3x dx. So this is our dot product. Now I can take back to the integral. All right? And the limits of the integral starts from 0 to 1 because it's only dependent on x, and we know from origin to point P, we are only moving from 0 to 1. And we are only interested in x because we expressed our dr in terms of x, or the path in terms of x. So that means that we have work, which is equal to the change in kinetic energy, is equal to the integral from 0 to 1, 3x dx. Now this is very elementary and it can be solved easily. We can write down as 3x squared divided by 2, all right, from 0 to 1, which is easily gives me 3 over 2 joules. All right, so this is our work. I shall have emphasized, or basically labeled, that these points are in meters, right? Meters. So they're physical. Okay. From 0 meter to 1 meter. All right. So we have 3 over 2 joule. That's our final answer. I shall finally emphasize two important points for the concept of work-kinetic energy theorem. First of all, if I write down again the equation, W is equal to delta KE, it's equal to integral from point 1 to point 2, force dot dr. My first point is that this force is not a single force. It's not a single force. It's a net force. All right. So this equation is not only valid for just a single force, but rather for a net force also. In fact, it can be always written as a general rule for the net force. That means we can write down the integral as this, or the right-hand side of this equation as the following. Or, more importantly, I can take out the summation outside to the outside of the integral, so I can write down that means we can take as many as works. All right, because we can see that each individual force that is acting on the object or the particle along the path dr can be summed. If we have more than one force, we have to use this equation. That means, in other words, we have to take out each or evaluate each f dot dr, all right, for each force, and then finally sum all the work values so that we can get the total change in kinetic energy of the system. All right, that was my first point. And the second important point is that if the net force is equal to 0, then that means that the change in kinetic energy, the kinetic energy is constant. All right, that is also because V is constant. Okay, that's another important point to know. If the net force is 0, then the kinetic energy is constant. Therefore, there will be no change in kinetic energy.